Now tell. Now am I audible to all of you?
Yes, ma'am.
Okay, okay. Others also, Jesleen, Shaima. Please turn on the cameras, all of you. So in the last class, what all have we studied? So we started with the formula of momentum's relation with kinetic energy. So we've basically seen that kinetic energy is directly proportional to square of momentum. So kinetic energy is equal to P square by 2m. P is the momentum, m is the mass. So this was one portion which we had seen. Types of work done also we have done. In types of work done, we've seen that positive work done is there, negative work done is there, and zero work done. Positive work done means our angle is acute. We'll get theta which is less than 90 degree and means 90 to 0 degree in between them. Then we have negative work done. Negative work done means your work done angle is obtuse. That is between 180 degree to 90 degree. So acute, obtuse. And zero means either it is 90 degree exactly, or your force is zero, or your displacement is zero. Something like this is zero, which is making the ultimate formula as zero. So this was what we have done. Conservative and non-conservative forces we have seen. So conservative forces are the forces which which are independent on the path traveled. They just depend on the initial and then the final position. That is what is meant by a conservative force. And if they do not depend upon just the initial and final point, if they depend on the path also, then we say the forces are non-conservative forces. All right. So I think we have to start with potential energy now directly. So I'll start. Now, potential energies concept is not just limited to your class 11's concept. You have to be very clear about potential energy because identification of potential energy is difficult. Like you'll not be able to identify the potential energy. As in, potential energy, see, kinetic energy when we were talking about. So kinetic energy came into system whenever you had any motion of the body began, you had the kinetic energy in the system, right? Now, if there's a potential energy, the obvious general and old definition of potential energy says that it's the energy whenever there is a change in the body's configuration. Like it's written also, energy possessed by a body due to the position, size, or configuration. But if you just go by this definition of position, size, and configuration, you will not be able to get your answers. Reason is that the definition of potential energy, whenever we are talking, it has a meaning with reference to the forces. All right, if the forces are not present, then there won't be any potential energy in the system. Means if two objects are present, they can exert force on each other. Now, exertion of force doesn't mean that you do not have, there has to be a force present. See, what is meant by potential energy? That's a different topic. I'll come to this again. Understand how to identify a potential energy. So, potential energy is basically identified by seeing if two objects are able to interact with each other. If two objects are able to interact with each other, then we say the potential energy is present. All right. Like two charges are present. Both the charges are able to interact with each other. Interaction as it means they are exposed to each other, they can interact with each other, and they can exert forces on each other. That is what is meant by electrostatic interaction in case of charges. So conservative interaction means whenever two objects are present, they are able to exert force on each other. Suppose two masses are present, two objects are present, they have their certain mass. So when both the objects are present, they are able to exert gravitational energy on themselves. So that will be the gravitational potential energy because they are able to exert gravitational force on each other. Two charges are present, electrostatic potential energy will be existing because they'll be able to exert force on each other, the electrostatic force. So likewise, you have the case wherever you see two objects are able to interact with each other. By interaction, what is meant by interaction? Interaction basically means both the objects are able to exert force on each other. If forces are present, then we say we have the energy which is potential energy. So it's not just the potential, and it's not just that potential energy is changed in configuration. Like if the size has expanded, so our potential energy is there. This is the only case. No, that is one case, but it's not like that is the only case present. If you see two objects are able to exert force on each other in somewhat manner, or just simple ways they are able to interact. How do you interact with someone? How do humans interact with each other? Like if I'm interacting with you right now, suppose Jesline is there, I'm interacting with Jesline. So it means we are in direct contact of each other. She can respond to me, I can respond to her. That is interaction, human interaction. Similarly, the normal literature meaning of interaction is only used here. This is not a physical meaning or some physics term used. So it's basically conservative interaction. So you have to be very clear about this. If still you have any doubts, you can always ask me regarding this. Because this topic of potential energy, this is not just here. It will come in your class 12th also. There everything will be repeated. And that time also it will be difficult. And why only class 12? Class 11th is also there. You have your gravitational potential energy. There also we'll be discussing it again. In fluids also we'll be discussing the potential energy again. So wherever two objects are exposed to each other, we discuss this. So that's why I'm saying be very much clear about the potential energy. Examples are also written. Conservative interaction. See, one example like gravitational potential energy. So when we are talking about gravitational potential energy, what is meant by it? Two masses are there. Suppose Sun and Earth, both of these are present. They are able to exert gravitational force on each other. Gravitational pull of Earth is present, right? So if they are able to exert gravitational force on each other, means Earth and Sun both are in direct contact with each other. They can interact. So they'll be having a potential energy. Fine. Now, electrical potential energy means if two charges are present in system. Then if these two charges are present, then how can we say that they are conservative interaction? Conservative basically means your frictional force, your viscous force, these dissipative forces are not there. That interaction. So potential energy will come in these cases only. Alright, so in your syllabus in class 11, also you have this, in class 12 also you have. So basically, the potential energy is also the change in the work done, or change in potential energy is change in work done. So all the entire work which is being done, this work done gets stored in the form of this potential energy. Now we have studied potential energy is there due to interaction. And what is meant by interaction? Interaction means forces are being exerted. Suppose these two charges are present. There is another third charge. So now three potential energies will be there because three interactions are possible. Two masses are present. They'll be having potential energy among each other. Suppose one more mass is there. So one more potential energy like this. So this is the whole concept of potential energy. Now work done against conservative force, it gets stored in the form of potential energy. Work done against the non-conservative forces. See, what are non-conservative forces? Path dependent and all that definition part we've already studied. But see, here this means whenever we say work done by non-conservative forces, basically the dissipative forces. And by dissipative forces, I mean something which is little wasteful. Like, see, if you rub your hands and you rub it like it, after a time, both of the palms will be hot. Why? Frictional force, right? So frictional force will come into action. So work done by non-conservative force, like frictional force, viscous force. Now, in the last class, I also told you about the concept of the whole system surrounding internal forces, external forces, isolated system. Means if this is entire your universe. Now, in this universe, there will be a portion which will be under observation. So this portion of universe under observation. This is your system. This is the system. Okay. Now, everything apart from this system, if you just delete the system from the entire universe, now whatever portion is left, this is your surrounding. Now, the thing which is important over here is that net force is 0. We call this as isolated system. I have told you this in the previous class, that's why I'm not repeating this in detail. So internal forces, forces within the system, external forces, forces outside the system. Like if I say a rocket is there. Now rocket is moving upwards. There's a force which comes into it. So this is the external force which is coming. But the internal force within the engine, this will act as the internal force. So these were the concepts which we have already discussed. Write it till here, then I'll discuss some. Okay, class. Now, let us discuss the work potential energy theorem. So, what was kinetic energy theorem? Work kinetic energy theorem. Justine, can you try? Work energy theorem. We have already discussed it, no? And we have been discussing it. So, it is what? Yes, Justine. What is work kinetic energy theorem? Yes, correct, Zainab. Change in kinetic energy is equal to work done. Change in kinetic energy is equal to work done. Very good try, man, Zainab. Jasleen, I don't know why you couldn't answer this. Have you not revised the previous class? You didn't unmute yourself. You didn't answer. Are you even present, Jasleen? I want your response, yes or no. If you're not present, I'll remove you from the meeting. So at least answer, na? I don't know, yes, no. Otherwise, how will I know in the online class when you all have shut your cameras now? So work done is equal to change in the potential energy. Initial potential energy. And one more thing, plus other students, only Jesting was the one who had opened the camera before also. Sabiha, Shaima, Zainab, this instruction is for you all. And I don't know why I have to repeat it in every class for this camera post. So see, there's point A, there's potential energy UA, there's this point B, energy UB. So change in the potential energy is UB minus UA, right? So this potential energy, this gets stored in the form, the work then basically gets stored in the form of potential energy. So this is called work potential energy theorem. So you have to be very careful whether it's work potential energy theorem or work energy theorem. Write down this to make a note point and write down this to, then I'll start with gravitational energy, the normal common formula mgh which you have been doing it. Because the formula is not just mgh, now I hope you know. It's equal to work done, and work done is force into displacement, so there can be any formula, right? So potential energies, but the standard formula which we have been doing, mgh, that we'll discuss. First write it down. Okay, class. Now the last part which is left, it is the gravitational energy. So see that MGH which you have been doing, that is just one portion. That is exactly one portion which we have been doing. All right. From all the energies which we are doing, just one portion is MGH formula. So do not see half mv square is definitely the formula of kinetic energy. Okay, half mv square is definitely the formula of kinetic energy. But MGH is not necessarily the particular formula of potential energy. Potential energy means the work done. So you calculate the work done by any method, all right, calculate it, and that will be the potential energy. It's just that you need to understand which 2 points are giving you that particular potential energy. So, yeah. So in gravitational potential energy, suppose a body is lifted from the surface of Earth. It's just lifted from the surface of Earth. Now the force acting is downwards, which is mg, right? Mg is acting downwards. You have a height h from the separation, that is from the ground you have it. So if you have height h from the ground, you have the force as mg. Now displacement is h, force is mg. It's very easy to calculate. Work done is force into displacement, right? Force is mg, displacement is h. Fine, force is mg, displacement is h. So work done will be mgh. Work done gets stored in the form of potential energy. So potential energy is mgh. This is just one case where the force is mg. All right, because it is work done only and work done is equal to mgh, that's why we are getting this in our final formula. So do not answer it quickly immediately that mgh is the formula of potential energy. No, that is the gravitational potential energy is one case. When you study gravitation, that time we'll discuss this. This is not just a this much small topic. It's an elaborated topic that we'll discuss. Okay, let me discuss this question too. See, class, always we choose a zero of potential energy. What is meant by zero of potential energy? That is a base or a reference line is present. All right. Suppose this is the base or reference line. Now from here I am calculating 2 kg mass is there. Downwards it will be having formula C. What is the formula? Formula is mgh, right? If the formula is mgh, so in the first part, this A part, delta U is equal to mgh, right? Mass is 2, G is 10, height is 5, so 15 to 200. So 100 joules, correct. But now in the B part, which is beneath, when this is the zero of potential energy, this is the reference line, this is the reference line. So this is minus 10. So same formula, mgh is present. Despite same formula, we will have height is, okay, it's 10 here. So the height will here be 2, 10 into height is minus 10 will be there. Means the potential energy will be minus 200. And see, in the C part, there is no displacement. So directly potential energy will be negative, will be 0. Why? Because it is mg into 0. There is no displacement. This is the mass, force. This is the displacement, which is, okay, write down this. Yes, yes, Zainab, you are right. G, this is correctly said that G will only be 10 if it is given. For our calculation purpose, for the class purpose, I use 10 for my convenience. Okay. Because many questions it is mentioned. In many questions, it is mentioned to take GS and then only take it. Right. You're correct.
Yes, because see, there is no displacement. Na? We are not calculating the distance. If the object was gone up, there was a distance covered, and then the body comes back to its initial position, then there is no displacement covered, right? That's why we say at exactly the zero of potential energy. It's like the origin of the graph. The axis, x-axis, there is no displacement over there. So we take it as zero. All right.
Okay, now coming to the spring mass system. So spring mass system is another case that you will get. So write it separately. That's why I've also written this. This is spring mass system. Fine. So what do you have to understand is the concept of this displacement and all. This is a spring, and towards this is the fixed end of the spring. It's fixed, and this is the free end of the spring. The free end has this block M, mass M, and this is the mean position. Mean position means the resting position, right? Mean position means the resting position. Now, if you extend it, so there is extension produced in the wire, means from the mean position, from the resting position, the block has been displaced. So we always calculate the distance from the mean position. So from the mean position to this point M, the separation is X. All right, this is the separation X, which we take. Now, due to the external force which was pulling it, like suppose I have pulled this block. So this is the external force which comes into the system. But associated with the external force, there is always a restoring force acting in the system. All right, a restoring system is always present, which is pointing towards the mean position. So see the block, so that the block comes back to its mean position. Similarly, here, if I compress it, so there's a compression produced in the spring. So again, I'll calculate the distance from the mean position. This is it. Now restoring force will act towards the right. Why? Because mean position is towards the right, so that it can go back. I have used the external force to compress it. Now the restoring force is in the opposite direction to compensate it. So all these I have told you. X is the displacement from mean position. F, restoring acts always towards the mean position. These are the two things which are important. Now see, direction of restoring force is opposite to that of mean position, right? If the mean position, basically we say that restoring force is acting in an opposite direction so that it can restore it. Restoring. So force is, firstly, it is directly proportional to minus of x. See, first part says that direction of the restoring force is opposite to that of mean position. Means C, opposite to that of mean position means C. I'll show you. See, this is the restoring force. Restoring force and mean position. Mean position is directed here, right? So restoring force is in the opposite side and acting towards it. It is always pointing towards the mean position. This is what is meant by this. So direction of restoring force is opposite to that of mean position means it is pointing towards mean position. All right, because mean position will be on the opposite side. That's why it has to change its direction. If you have extended the block or compressed it, so f is directly proportional to minus of x. This is one point which you have to remember. Okay, what is x? X is the restoring force. So f is equal to minus of kx. We use the formula. X is the displacement from the mean position. This is the displacement from the mean position. This is the force. And this is a spring factor, which is possible and present in different systems. Like in the spring mass system, we say this is the spring constant. So this is the separation. All right, this is the way we have been calculating this. So F is directly proportional to the displacement. This is 1 point, and negative sign shows that it is directed towards the mean position. That is in opposite direction of the mean position. All right, start writing this from here. Yes, it's the internal force. External forces which we are pulling it. And a restoring force is the internal force which automatically develops so that the body comes back to its equilibrium state.
Ma'am, can you scroll up? Ma'am, can you scroll up?
Now it's audible. Please check. Now it's better. Yes,
Ma'am, your
no.
voice is really low.
Now also it's not audible.
Yes, ma'am, now it's audible.
Now it's audible. So I was saying from x equal to 0, x equal to x, the block has been extended and there is this external. So we write the work done f dot dx, that is from 0 to x. We have to integrate it. Now one more thing, work done here, it will be f dx cos theta, right? This is what we are integrating from 0 to x. Now our theta, this is 180 degree. So integral of minus f dx from 0 to x will be left. This is the first step which you have to remember.
All right. Now the second portion here is
you are just solving this. So work done is basically minus kx. We are writing the value of force as kx, right? Kx dx integral from 0 to x. Now when you are solving it, minus k will come out. This becomes x square by 2 from 0 to x. So if you just put the values of minus k, so first x square will come minus 0 square by 2 will come. So what are we left with? Minus half kx square. All right, minus half kx square. Now the total potential energy, this is what? This is the internal work done. We know that internal work done and external work done, they are negative of each other. So this is the work done through internal force, right? We were using internal force only, right? So this is internal force. So delta U is equal to minus work done of internal force. So minus, what is work done by internal force? Minus kx square, right? So change in potential energy becomes half kx square. This is the formula of potential energy. What are the things which are present? What is delta U? This is basically the change in potential energy. K is the spring constant. Spring factor means any constant can come for any system, but if I am saying spring constant means specifically for spring mass system. And what is X? Displacement from the mean position. So this is displacement from the mean position. All right, write it till here. If you've completed, please text me done in the chat column, class.